Question 5. Part A. A student uses a plotting compass to investigate the magnetic field around a wire. Figure 10 shows the wire going straight through a card. Figure 10 shows the compass needle when there is no current in the wire. Which of these shows a possible direction of the compass needle when there is a current in the wire going from P to Q? So the current is going from the bottom up to the top. Right, well at the minute, that's just lining up with the Earth's magnetic field. However, as soon as you get a current going through a wire, you end up getting the magnetic field going around the wire. Now we use the right hand grip rule. I've got a lovely video all to do with currents going through wires. Click the link above. We use the right hand grip rule to work out what's going on. Your thumb represents the current and your fingers, as they curl around, they would curl around the wire. They would show you which way the magnetic field is travelling. So the magnetic field will be travelling around the wire. If we were looking down on top of the wire, that would be in an anti-clockwise direction. So this compass is going to point over. Since the compass is here, the compass is going to be pointing over there. If they put the compass here, the compass will be pointing there. If they put the compass here, the compass will be pointing there. If they put the compass here, the compass will be pointing down there. So since the compass is there, it's going to be pointing over to the right. So that's this bad boy. There we go. And like I say, check out my video if you don't understand what's going on with currents going through wires. Part 2. Describe how the student could develop the investigation to find the shape of the magnetic field produced by the current. Well, it's just what I've said over here, isn't it? If they were to place more compasses around the wire, and then if they could follow the direction of the needle and draw that down, that would show you the shape and it would show you the direction. If you wanted to add more to that, if you were to sprinkle little iron filings, now because iron is a magnetic material, if you were to tap the card, then all of the iron filings would line up with the magnetic field around the wire. Once again, I've got a lovely video that'll show you how to do this. Click the link above. That says needle. So 1 mark for saying placing many compasses around the wire. 1 mark for saying draw arrows to show the direction of the magnetic field, and that would be shown by the compass needle. And then connect the arrows together to show the shape of the magnetic field. Or like I say, you could sprinkle some iron filings around the wire to see the shape. So you definitely get 3 marks for coming up with an answer like that. Part B. Figure 11 shows a copper wire between 2 magnetic poles. The current in the wire is in the direction shown by the arrow. The wire experiences a force due to the magnetic field. The direction of the force due to the magnetic field is it up, down, or blah, blah, blah. Right. This is Fleming's left-hand rule. I've got a lovely video to show you in detail using 3D animation how this works. I suggest you check it out if you don't understand what I'm about to say. So we can see the direction of the currents going this way. We know that the magnetic field It always travels from north to south, so the magnetic field is travelling along this way. And we need to know which way it's going to move. Now, Fleming's left-hand rule looks like this. That's supposed to be your left hand. That's your thumb, which shows you which way the wire is going to move. And that's because of the force. The first finger shows you which way the magnetic field is. Now your knuckles are north and your fingertips are south. So the magnetic field always goes from north to south. So we know it's going that way. And then your second finger shows you which way the current is flowing. So you'd have to point your your second finger so it's coming out of the computer screen at your body, because that's the direction the current's going. Now that's convenient because your first finger should now be pointing from left to right across the screen, and that means that your thumb is left pointing upwards. So that means that the wire is going to move upwards, and in which case the answer is B. Fleming's left-hand motor rule can be tricky, so like I say, check out my video. I'm quite proud of it. I'm getting into 3D animation, and that's what I'm going to do with my videos. And some of that video is one of the first ones I've done with 3D animation, so check it out if you want. Part 2. The interaction between the magnetic fields produced by the magnet and the current in the wire produces forces on the magnet and the wire. Compare these forces. Right, this is Newton's third law. For every force is an equal and opposite force. So this magnet is putting a force on the wire which is making it move upwards. Now, for every force is an equal and opposite force. As that wire is moving upwards, it would put a force on this magnet moving downwards. However, this magnet is a lot bigger and it'll be placed on a flat surface, so it's not going to move, is it? So you normally don't recognise that that's happening. But that's the answer and that's the reason. So the forces are equal and opposite. Now it's only worth 1, but if it was worth 2, boom, nailed it. Part 3. Figure 12 shows a different wire inside a uniform magnetic field. The magnetic flux density of the magnetic field is 0.72 newtons per amp meter, or in other words, Tesla, if anyone's into their cars. So that's B. The length of the wire inside the field's 30 millimeters. Right, well that's L. Now we're going to need to convert that into meters. The size of the force due to the magnetic field on the wire is that many newtons. So that's F. Calculate the size of the current in the wire. So I is what we're looking for. Use an equation selected from the list of equations at the end of this paper. Right, we're looking for an equation that's got B, L, F and I in. Now I know what it is straight away. I've got a video that shows you all the different equations you need to remember. Click the link at the top. Right, so if we're looking down the list, there it is there. F equals Bill. Now just be careful, they do a lowercase l, not a big capital L. Right, we're going to have to rearrange that to get I. So, nice way to rearrange it is put a big line under there, put a line under there. I should have drew the whole thing over here a bit more. Right, we need to get I on the top, which it already is, and now we need to get it by itself. So if I take B across to this side, now remember, as it crosses over the bridge, as it crosses over this equals sign, it's also got to cross this line here. So B would end up on the bottom. Next I need to get L on over to this side, so I'll move it over here, and then because it's crossed the bridge, it's also got to cross the line, so it'll end up down here. Now if I just rewrite that so it looks neat, and now I'll pop the numbers in. Hang on, first I'll convert that. So 30 millimeters, if I divide that by 1,000, that'll come out in meters. And you know the best thing to do when you're dividing something by 1,000? Just stick a times 10 to the minus 3 on the end. And that's the easiest way of getting yourself confused like I just have. Anyway, let's get back to that. So that would be 0.045 newtons divided by 0.72 times by 30 times 10 to the minus 3. I'll just pop the numbers in. Recurrent. And I'll just round that up to 2.1. Question 6, part A. A teacher is demonstrating electromagnetic induction. The teacher has a bar magnet, a coil of wire, and a sensitive voltmeter. Draw a diagram to show how the teacher should arrange the apparatus. So electromagnetic induction is about making an electric current by using a magnet. So if we take a coil of wire, or take some wire and coil it, and then if we hook that up to a sensitive voltmeter, and all we need to do is take our magnet and pop that in and out of the coils, and that'll get you the 1 mark. Part 2. Explain how the teacher could use this apparatus to demonstrate the factors affecting the size and direction of the induced potential difference, so the induced voltage. Right, well, the size of the induced voltage is affected by the speed that you're moving the magnet. If you move the magnet fast, you should end up with more voltage. I'll just put PD for potential difference. And if you were to move it slowly, you'd end up with a small difference. If you have more coils, you'll end up getting more induced potential difference. And less coils would induce a smaller PD. What you could also do is when you shove the magnet in, you'll end up getting perhaps a positive voltage, and then as you pull the magnet back out, you'll end up getting a negative voltage, so you could change the direction of the magnet. Reversing the direction will reverse the PD. And finally, instead of putting the south pole in, if you were to reverse the magnetic field and put the north pole in, that would reverse the induced potential difference. And these are all the different factors. So you'd easily get 4 marks by answering like that. Part B. There is a changing magnetic field in the core of a transformer. Describe the cause of the change in magnetic field in the core of the transformer. So first of all, let's understand what a transformer is. It's basically a laminated iron core, and then you've got a primary coil, and then over here you'll have a secondary coil. Now transformers only work by putting an alternating current in. Now we saw in a previous question, if you place a current into a wire, you end up with a magnetic field around the wire. Now alternating current means that first of all, for a split second, the current would be coming in this way, and then a split second later the current would be coming in this way. So the current, the flow of electrons, is reversing every split second. So as the current reverses, the magnetic field would reverse. So the reason you've got a change in magnetic field in this core is because of the alternating current creating a change in magnetic field in this primary coil. So an alternating current in the primary coil causes a change in magnetic field around the primary coil, which causes a change in magnetic field in the transformer core. Transformers can be tricky, so make sure you understand how they work. Part 2. A potential difference of 230 volts is applied across the primary coil of a transformer. There is a potential difference of 15 volts across the secondary coil. The primary coil has 2000 turns. Calculate the number of turns in the secondary coil. Use an equation selected from the list of equations at the end of this paper. Right, let's have a look at that then. There we go. The voltage across the primary coil divided by the voltage across the secondary coil is equal to the number of turns in the primary coil across the number of turns in the secondary coil. In other words, a ratio of the voltages in the two coils is equal to the ratio of the number of turns on the primary and secondary coils. Now, we need to calculate the number of turns in the secondary coil. So that's NS there. So the first thing we need to do is we need to get NS on the top. And then we need to get it by itself. Now probably the easiest way to do that in this case is if I just flip this right hand side, that'll get NS on the top. Now remember, whatever you do at the right hand side, you've got to do it to the left hand side. So we could rewrite it by saying Vs over Vp is going to be the same as Ns over Np. Now that we've got Ns on the top, we just need to get it by itself. So I need to move Np across to the other side. So if I move NP across to this side over here, and then remember, as it crosses over to the other side, it also needs to cross the line. So it's going to end up over here on the top. And remember to cancel that out. So if I rewrite that, just to make it neat. Now if I pop the numbers in, and that comes out as 130.4. So that's just 130 turns. Now if you don't know what's going on here, let us just draw a sketch for you. Now the information that it originally gave us said a potential difference of 230 volts is applied across the primary coil. So this has got 230 volts, the voltage on the primary. There's a potential difference of 15 volts across the secondary. So the voltage on the secondary is 15. Now it told us that the primary coil's got 2000 turns. So the number of turns on the primary equals 2000. And we needed to work out the number of turns on the secondary. Now you've either got a step up or a step down transformer. Whatever the transformer says it does, that's what it does to the voltage. So you can see here that the voltage is getting stepped down. So this is a step down transformer. Now you know it's a step down because the voltage is getting less. Now if the voltage is getting less, the number of coils will get less proportionally as well. So if we can work out how many times less the voltage is getting, that'll tell us how many times less the turns we're getting. So one way of doing this, we could just go 230 divided by 15. So that equals 15.3 recurrent, so 15 and a third. So basically the voltage has got 15 and a third times smaller. So that means that the number of coils is going to get 15 and a third times smaller as well. So if we do 2000 turns divided by 15 and a third, so 15.333333, that equals the 130.43, which is what we got using the other method. And that would be our NS value. I've got a nice video all to do with transformers, so if you want any more information you can click the link above. Question 7. Want to see more videos like this? Subscribe to my channel, GCSE Physics Explained. Thanks very much and bye for now.